Okay, this is for lab number 1 for Astronomy 400, and we're going to basically, this would be your Canvas page. I've got it in student view, so you would go to modules, you go down to Astronomy 400 Labs, so there you have it right there as a window document. You click on this, and when you click on it, you should get this. Okay, Astronomy 400 Lab, learning the planets through Stellarium. And then when you're all done with it, you come up here, online assignment, click on that. So this is the actual lab right here, Astro 400 Labs online assignments. This is where you turn them in. So you click on that, you're all done, submit assignment. Okay, so you just go submit assignment and browse, and you want to turn it in either as a Word file or a PDF. Okay, so that takes care of that. Now the lab itself. So, learning the planets through Stellarium Part 1, the terrestrial planets. I was going to have both the terrestrial and the Jovian planets on this one, but this was taking me too long to do. Okay, so down here, you've got a list of objects that are in our solar system. Start from the closest planet, that would be Mercury. You got Venus, got Earth, where we live, okay? The moon orbits the Earth. You got Mars, you got the asteroid belt. So they're giving you one example, one asteroid out of the thousands that are in the asteroid belt. Then you go out past the asteroid belt, now you're into Jupiter, the Jovian planets, big huge gas balls, Saturn, Uranus, Neptune. We get out to Pluto, which used to be a planet but got demoted, and now it is simply maybe one of the biggest members, if not the biggest member of the Kuiper belt. We don't know that much about the Kuiper belt to know. I think it's one of the biggest. I mean, I know it's one of the biggest, but is it the biggest? I don't know yet. Hale Bopp is a comet that visited Earth not too long ago. And you got the Sun, the most dominant object in our solar system. Now, AU stands for astronomical units. Okay, you see the AU there? That's astronomical units. That's the average distance. One astronomical unit, 1.0 astronomical units, is the average distance between the Earth and the Sun. Got to get a drink of water. Hold on. Okay, as I was saying, one astronomical unit is the distance between the average distance between the Earth and the Sun. Sometimes Earth is a little bit closer than that, like 0.98 astronomical units. Sometimes a little further than that, like 1.02 astronomical units. But right around 1 astronomical unit, that's the average distance between the Earth and the Sun. So you can see the other planets are closer, Mercury and Venus, and then Mars is further out, and then you get way down here to Neptune. Neptune's 30 times the distance from the Earth to the Sun. Okay, that's what an astronomical unit is. And then orbital period is how long in Earth years it takes the planet to orbit the Sun. So there's Earth at 1, because that's what defines a year. How long does it take the Earth to orbit the Sun? You can see that Mercury is down here at a quarter of a year, just about 4 months. Again, Venus would be maybe like about 7 months or something like that, 8 months. And then you come down here, Mars takes about 2 Earth years to orbit the Sun. Jupiter takes almost 12 Earth years to orbit the Sun. You go down here to Neptune, 164 years to orbit the Sun. You notice any relationship between the planet's orbital periods, this column here, and their distance from the Sun, this column here? Well, let's see, you can kind of look, and hopefully you're seeing a pattern here as you look at them. One number is increasing, the other number is increasing, or both numbers are decreasing. So you want to write down, what did you notice there? Okay, hopefully you noticed something already. It's not too hard to notice. All right, now this looks complicated. Believe me, I just wanted to show people this who may have a little bit more interest in mathematics than a lot of people do. But basically, all we're going to do is we're going to try to figure out how many of planet Earth's could fit inside the volume of Jupiter. Okay, and it's not that complicated. You simply take the volume of Jupiter, and you can approximate Jupiter's volume by using the equation for a sphere. It's not a perfect sphere, but we don't want to be we don't want to get that mathematically involved. All right, so all you simply do is you take the volume of Jupiter and divide it by the volume of the Earth. Okay, and that tells you how many of these volumes would fit into that volume. But if you notice, a lot of these things are the same. They'll cancel out. The 4/3 pi will cancel out. The Earth cubed will cancel out, Earth cubed will cancel out. We'll be left with just 11.2 cubed. 11.2, if you look up here, that's how many, that's in this column here, Earth radii. So that's how many more larger Jupiter's radius is compared to Earth. So you could fit just about 11 Earths across the diameter of Jupiter. But then again, that's just a diameter. That's not the whole volume. So how many Earths could we fit inside of Jupiter? You're simply cubing this. So you got 11.2 to the third power. You get 1,405 Earths could fit within the volume of Jupiter. So we just took the radius of Jupiter, cubed it, and that gave us how many of our planet could fit within the volume of Jupiter. So to find the number of planets the size of Earth that would fit inside the volume of Jupiter, we simply cube the radius of Jupiter. Using this final equation, just use this one right here. Okay, calculate how many Earth-sized planets could fit within the volume of Saturn. Well, you come back up here, and you've got the radius. You go down to Saturn, and then there's Jupiter 11.2. You got the 9.5 for Saturn. Okay, so this is a very easy calculation. You should be able to do it. I mean, you're in college, so you got to be able to do stuff like that. Okay, now this is apparent magnitude. Okay, this is how bright. It's a comparison of how bright objects appear on the Earth. Now, astronomers do things so differently. You're going to find that. You probably already found it out in the lecture class. But very, very large positive numbers are very, very dim objects. In other words, if their apparent magnitude was around 30, it's barely what Hubble can see. Okay, the Hubble telescope, the one we put up above the Earth's atmosphere, the great technology. If you're up there with an apparent magnitude as seen from Earth, you'd have to put the Hubble up there and barely see it. Telescopes with CCD detectors were down to 26. 4-meter telescopes, okay? That's a pretty big telescope. Now, the more that we might be able to buy in a store, a 25-millimeter telescope gets us down to 14. A nice pair of binoculars, you can see things as dim as plus 10. Bernard star, one of the closest stars to our sun, that's a 9.5. Naked eye limit, if you have incredibly great eyesight, you can see things as dim as plus 6, okay? So Polaris, we can see that with the naked eye. That's a 2.5. Betelgeuse is even brighter than Polaris. Now again, like I said, now we're going into minus numbers. That's the brighter ones, minus 0.8. Sirius, minus 1.5. Venus at its brightest, minus 4.4. Then we got the full moon. You know how bright a full moon looks. That would come in on the scale at a minus 12.5. The sun's the brightest thing in the sky, period. It's minus 26.7. Okay, so you can see that that's how the scale works. So the very, very, very bright ones are big, huge negative numbers. The very, very dim ones are very high positive numbers. And a lot of things we see normally in the sky are in this range right here. Okay. So it tells you what apparent magnitude is. It's how bright the object appears from the Earth, and this just goes over the same things I just talked about. Okay, so we want to open Stellarium. I already have Stellarium open here. Okay. Okay, and locate Mercury. Okay, and then watch the Stellarium video. It's one of the YouTube videos that's on there on my channel that will help you learn how to use it. But anyway, so I'm going to assume you've watched that video and you've messed around with Stellarium at this point. So here's Stellarium. We want to first of all get the location. So there's the locator. And I put in Mercury. So I have located Mercury. Now, over here, you've got, this just says magnitude. It doesn't say apparent magnitude. That is the apparent magnitude. So that's how bright Mercury would appear from the Earth, okay? So it would put it someplace in here. Okay, brighter than Polaris, but not as bright as Betelgeuse, I guess. So that would be where Mercury would be right now, as we speak right now, though. Because Mercury goes close, far away, close, far away. So it's at different distances from the Earth as we both orbit the Sun. All right, so if you take a look here, down here, you've got its magnitude. Now, absolute magnitude, I got to figure out why it's saying that Mercury would have a greater absolute magnitude than apparent magnitude, because absolute magnitude is how bright it would appear if it was 10 parsecs away. Well, Mercury is way closer than 10 parsecs away, so this is its apparent magnitude. I'm thinking it's an absolute magnitude. It has to be way, way, way less than this. A big positive number, as a matter of fact. Something we can't even see if it's 10 parsecs away. So I think they must do planets on a different scale. I've tried Googling it to try to figure it out. I can't. I'm going to email Chris Taylor, who's the astronomer, who's a chair at Sac State, see if he can explain this to me. But for now, let's just forget about absolute magnitude for planets, because I don't understand why it's got that number there. Look at this number, 0.66. Okay, so the apparent magnitude, how bright the object appears from Earth, is 0.66 for Mercury. So this is over here on Stellarium. Look up here. There you've got type planet. You've got the magnitude 1.23. Okay, oh, see, now it's changed. Why does it change from the one I had? Because this is real time. Okay, let me just here. Watch what's going to happen to this number right here as I go through time. See, now it's 1.28, 1.29, 1.3. So it changes over time. So if you go back to when I might have made this, how long did I make this? So now you can go see it's going down to where it was. So you see this number here changed a lot. Okay, and I can go back to, so now I just want to go back to the present. Okay, so this should be right now. So right now it's 1.23, but when I captured this picture, it was down at 0.66, which was probably a couple of days ago now. And you can see that if I went backwards in time, you can see Mercury did do that. Let's do it again in case you didn't get it. So this number here, right now, on the handout it says 0.66. Remember, that's going to depend on how close or how far Mercury is from us. So let me go backwards in time. Okay, so let's go faster then. There, look at that. Now it says minus 0.60. So however long ago that was, it's probably close to when I took this picture, where it was 0.60. Well, actually that says minus 0.60. All right, so anyway, let's go on from there. So the apparent magnitude is 0.66 for Mercury at the time I captured this picture from Stellarium. Now to find the distance, we go down the list. You see there's distance to Earth. This one actually tells you distance from the Sun. Then the other distance is telling you it's distance from the Earth. So going back to Stellarium, we put this, I think we're back to right now. You go down here and you got distances. There's distance from the Sun. So right now, as we speak, it's 0.449 astronomical units from the Sun. It's 0.7 astronomical units from the Earth. Okay? So that's the distance between us and it. You go back over to when I captured this, which was actually not too long ago, I don't think. So this is 0.701 astronomical units from the Earth. It's going to stay pretty close to 0.449 from the Sun over a short period of time. This will change, but it'll stay pretty much the same. Now from the Earth, it's changed from being this far, 0.701 to 0.700. Okay, right there. So let's watch these two numbers. Let's actually watch just the Earth number. That'll be more interesting. The Earth number right here. Let's go through time. So we should go forward in time. What the heck? 0.69, and there it goes. Look at it going. Getting closer to Earth. We're in our orbits, remember. So as we go through our orbits, we're going through time, and you can see we're getting closer and closer and closer to the Earth. And now as we pass, it'll start going back up again. So we're getting close to our orbits. Let me go a little faster then. We're already going back up in time, okay? Go back to normal, go back to right now. See, this goes back to normal, this goes back to right now. Okay, normal speed, then right now. Okay, so that's how we can find the distances to Mercury from the Sun and from the Earth. Now we go to Venus. You can find Venus a couple of ways. First of all, Venus and Mercury are both going to stay very close to the Sun. Because they're closer to the Sun than the Earth is. So in the sky, to us, it looks like they follow. So there's the sun way over here. And there's Venus right there. Okay. As a matter of fact, if you go through time, let's do that again. We can actually, let's just go way out. So Venus is over here. Mercury is over here. And we can play around the time again. Let's go really, really fast. Oh, I didn't. Whoops. Guess what I didn't do? I did not. Hold on. Okay, now I'm centered on the sun. Mercury is there. Venus is going to be someplace close by. There's Venus right there. So there's Mercury, there's Venus. If we put the Earth up, you see what's going to happen. They kind of set together. What happened? I put the Earth up. So, whoa. Okay, we don't have the right time here. Okay. Okay, here's the Earth. Here's the sun. Here is Venus is right here, and Mercury is up here. So if I come down here and I go increase the time, you can see that as we go through tonight, it's the 11th. It's about 4. It's actually 2 o'clock, almost 3 o'clock. Okay, let me make it go a little faster. There you can see the sun sets. We can still see Mercury now. Mercury's gone. So they kind of go together, all right? And then there's the sunrise the next morning. And so you can see Venus and Mercury, as seen from Earth, go around this, go around the Earth with the sun. Okay, let's go back to now. Let's get rid of the Earth. Okay, so now let's go to Venus. Go in. There's Venus right there. Then I can center on Venus. Now we can go way in. Okay, so Venus is the second planet from the sun. It is almost as large as the Earth. Venus has a very dense and hot atmosphere. The surface temperature on Venus is 880 degrees Fahrenheit, something like 600 something degrees Celsius. That's over 8 times hotter than the hottest Sacramento day. Even when it gets to be 110 times 8 is 880. So think about the 110 day. Imagine it being eight times hotter than that. Okay, I don't want to even imagine that. So what is the apparent magnitude for Venus? Well, just like we did for, if you take a look over here, there we got this. We got it for Venus. You've got your distances down here as well. Okay, so we already looked at those. You got your distances, you got your magnitude. Okay, now next we want to take a look at Mars. Okay, so we simply go back to Stellarium. Now we go to locator and we type in Mars. M-A-R-S. And there's Mars. And I just thought of something. Oops. Hold on. Okay, what I did was I added this. I meant to do this sooner, but it wasn't until I saw Mars I remembered I forgot. Mars has a nickname. It is also known as the blank planet because of its color. What is Mars's full nickname? The blank planet. So, I'm going to just write in what its number is just by, if you look at Mars, what would you get? Okay, green planet, blue planet. So that's basically the nicknamed question there. So here's Mars. You simply, now here's another thing we want to do. It's got 2 moons. Of the 4 terrestrial planets, Mercury, Venus, Earth, and Mars, Earth has 1 moon, very famous moon we know about, but Mars actually has 2. Now they're very, very small, okay? They may just be captured asteroids. I think that's what they are. They're just captured asteroids. They're nowhere near the size of our moon, okay? So they're very, very small, but they're called, you can see their names because that's a question there. So weak and I just messed up big time. Okay, let's go back. Let's, I don't know what I'm on here. Okay, we got Mars centered again. Let's go back in. Okay, so we can go in and we can click on Phobos and make sure we're centered on that. Okay, so we can go pretty far in here. Maybe not too much further. Then you got the other one down here. We can click there and center on that one. Okay, so anyway, you can see the 2 moons, and you can go back. We can focus on Mars, and we can center on Mars, and then we can go in and we can go ahead in time. We can watch their orbits over time. Okay, usually we don't learn too much by going that fast, but you can go through slowly, see how fast the time's going up. 21 hours, 22, 23, 24, so we're going pretty fast. I can slow it down a little bit. Oh, I sped it up, didn't I? Okay, so now we can see how it goes through. You can see how the moons move relative with the time and how they orbit Mars. Okay, so let's go back to now, and let's go back to the lab. Okay, zoom in on Mars, find the moons, what are their names, draw a picture of Mars and its moons, be sure to label Mars and its moons. And notice if you don't see one of the moons, just go ahead in time, because if you take a look, one of them could get hidden over time. It's because it's behind, it might go behind Mars from our vantage point. So you can see that as time goes by, that not quite going behind. No, I guess from our vantage point for a long time, but so they just barely miss. Okay, so that's good. But in case that happens, I didn't go that far into the future. In case that happens, just do that. Okay, so then you just how far is Mars from the Sun? So you know how to do that. How far Mars? That's the whole lab. That's it. Okay, so you just type in. Oh wait a second. Draw. Maybe you can use. I'm just thinking. Well, hold on a second. I got to think about something. Okay, if you have the means to draw Mars into 2 moons and embed it in here, that'd be great. If you don't have that, maybe you could just type in why you couldn't do it, or you don't have the technology to do it. Anyway, so I forgot about that. That's going to be a problem, I think. I don't know. Okay, so there's the lab. Let me shut it down now. I hope it's not too long. So I'm going to pause now, say good night, good afternoon, or whatever it is where you're